Greetings. I'm Mr. French, and I'm coming to you from my classroom in Mount Pleasant, Utah. And this is our follow-on video for topic 3.3, differentiating inverse functions, where I'll be going over some examples. So let's start by remembering what we discovered about functions and their inverses and their derivatives. We determined that if in my original function f, I had the point a comma b, that meant that in my inverse function, I must have the point b comma a. Our x and y values are reversed. And if I looked at the derivative of my original function at a and got some value c, well then the derivative of my inverse function at the b value, the output of my original, was going to be the reciprocal of my original function. So I'm going to try and use that relationship to answer these following questions. Here I have an increasing function, g, that satisfies g of 3 equals 7. So g is my original function. G inverse is going to be what we're going to discover information about. So I know I have the point 3, 7. When the input is 3, the output is 7. And my derivative at 3 is going to be 5. Well, that means that my input in the inverse is going to be 7, where my output will be 3, and my derivative at 7 is going to be the reciprocal of my derivative at 3 in the original function. So I can say that g inverse of 7 is equal to 3. When the input is 7, the output will be 3. And the derivative at 7 is going to be the reciprocal of the derivative of the original function at 3, so 1/5. So g inverse of 7 is 3, and the derivative of g inverse at 7 will be 1/5, the reciprocal. Let's look at another example. Okay, for these 4 possible functions g, for which one would the inverse derivative at 5 equal 1/7? Well, if 5 is the input for the inverse, then it must be the output for the original function g. So g of a is going to equal 5. And since the derivative inverse at 5 is 1/7, then g prime of a must be the reciprocal of 1/7, or 7. So all I have to do now is figure out what a value we're talking about for each of these 4 functions. I know that each function has to equal 5. Once I find out what x value will allow that to happen, I can take the derivative at that x value. Well, actually, if I look at the first function, I know that it doesn't matter what a value will work, because the derivative of a line is the slope of the line. Our slope is -7, but I need a slope of 7. So we can eliminate our first choice. Now, 3x squared minus 5x plus 3. Well, 0 won't work, and 1 won't work, but 2, 3 times 4 minus 5 times 2 plus 3 does equal 5. So if I look here, I'm going to find out what g prime of 2 is for my second function. Let's just label these A, B, C, and D. So for B, g prime of 2, using our power rule, would be 6x minus 5. Well, if x is 2, that's 12 minus 5, which gives us 7. And that works. So we've found our answer. Let's take a look just quickly at C and D to see why they might not work. So for C, 3x cubed minus 6x minus 7. Let's try, well, 1 would be 3 minus 6 minus 7. That's much too negative. 2 would be 3 times 8 minus 6 times 2 minus 7. So that's 24. So B actually doesn't work, or it did work at 2. So 24 minus 12 minus 7 does give me 5. So we are looking again at C prime of 2 to see if it's equal to 7. So C prime, the derivative of 3x cubed, is 9x squared minus the derivative of negative 6x, which is just minus 6, and then 0 for the derivative of negative 7. So if we put 2 in there, we get 9 times 4 minus, which is 36, minus 6. So that's 30. And that is definitely not 7. So you can see how we are able to find our magic equation because we knew that the output had to be 5, and then the derivative at whatever input created that output had to be equal to 7. Let's look at a third example. F and g are inverse functions that are differentiable for all x. If f of negative 2 equals 3 and g prime of 3 equals 4, what can be said about f prime? Well, since f of negative 2 equals 3, then we know that a is 2, negative 2, and b is 3. And we know that for g, the inverse, the input will be 3, and the slope is 4. Well, if the slope is 4 on the inverse, then the slope on the original must be the reciprocal of 4, or 1/4. So we can say that f prime of negative 2 will be the reciprocal of g prime of 3, 1/4. We also know that these two functions are differentiable for all x. We don't have a restricted domain to create inverse functions, which means that our two functions have to be monotonic. They have to have the same behavior, no changes in direction. And since we know that at one point our derivative is positive, or our graph is going up, then the graph must be going up for every value of x, which tells me that the derivative, if I take the reciprocal, it's not going to change sign. And our derivative of our original function f must also be positive for all x. All right, so just a quick recap. If I have the points a comma b on my function, then on my derivative, I will have the points b comma a. And if the derivative at a in my original function is c, then the derivative at b in my inverse function, so g prime of b, will be the reciprocal 1/c. And those are our examples for topic 3.3.